Yes, it works. So once more, what we are discussing from the last lecture is global effects. I mean, we have an organic synthetic reaction and we would like to isolate the product from that, and we must follow some general rules, some of them rules of thumb, and we discussed especially last week such terms as the uh, stereo or chemo or regio selectivity and specificity of the reaction, which should be as high as possible, basically, because the higher the selectivity or specificity of the reaction, then we can have the more pure product, and then it costs us not so much effort, money, and so on. And then what is important is a number of steps in which we can isolate the product. So these numbers should be as low as possible, because with the increasing number of steps, the yield of the reaction decreases, and then of course it costs us more money, more effort to isolate the product, and so on. And then is something like control of the reaction. Basically, from chemistry, we know two types of control. First is thermodynamic control, and then kinetic control of the reaction. So it's not the same, and we of course would like to have kinetic as rapid as possible, not to spend too much time, and we also would like not necessary to have a thermodynamic to interfere, let's say, to stop the reaction somewhere between the products and the reagents. And in that context, what has been recently proposed is so-called inflow chemistry. And we'll discuss this. In flow chemistry, it means that we can put reagents into, let's say, a tube, and the speed of flow of reagent can be controlled, and even we have in the reaction zone these reagents spending so much time as we would like to. So we can control the reaction proceed, and it is very interesting, and we have here the product, of course, of that reaction in flow chemistry. We'll discuss that, but not necessarily today, and next weeks of those lectures. And then another type of control is something that I say is technical control of the reaction. So then if we have here reaction yield, and here we have parameters, so we can have such a sharp control. Let's say we'll need 105 centigrade to have a high yield, and then we have a plateau type of control, the second reaction. So a first reaction, the second reaction, a plateau like. So let's say between 20 degrees and 300 degrees, we have always 100% or 90% of the reaction yield. So of course the better situation is such with this plateau control, because we can come to the lab, we can have a coffee, and the reaction is going on. So much easier to be controlled by the operator, by the chemist sitting in the lab. And then, of course, we are realizing that there are many obstacles in the contemporary society, in the contemporary environment in which we must work as chemists, as organic chemists, and these needs to design synthetic approaches, organic synthesis in such a way not to disturb our environment. It's called, let's say, green chemistry. And of course, we have some rules from green chemistry which we should follow. So, for example, it's not a coincidence that almost all chemistry or drug, let's say, synthesis has been shifted to China. Because in the States, for example, United States and in Europe, the environmental protection rules are so strict that it would cost much more money to produce the same product. And of course, economy, as we discussed during the first lecture, is probably the most important parameter that control our industrial activity and any form of human activity. So we have, let's say, 12 rules of green chemistry which we should follow very strictly and which should be our priority during designing or of any synthetic approaches, regardless of that it's in laboratory or in the real industry. Of course, in lab it's a little bit less important. If we are synthesizing tons of products, then it will cost us much more environmental pollution or environmental problems. Okay, so let's see these rules. We should discuss them because today we cannot get rid of that in any form or chemical activity. And first is prevention. Which simply says it's better to prevent waste than to treat or clean up waste after it has been created. So we should realize that chemical synthesis will give us not only the desired products but also some byproducts, not necessarily coming from the stoichiometry of the reaction. I mean, not necessarily from this non-selectivity or non-specificity, but coming from the solvents, coming from other different auxiliaries that we are using. So we have, for example, 100% of yield, and anyway will become some waste which we should then treat. So prevention. It's much better to think of it before reaction, before designing, before coming to the lab, than just performing the reaction and then thinking, okay, what's that? So we can see, for example, that even in not chemical activity, let's say in power industry, so where we are generating power electricity, let's say if I built, for example, a large electric power station in Poland, Ostrołęka, which costed, let's say, 1 billion zloty, more than 1 billion zloty, and now okay, we don't need that because we are creating too much byproducts, or let's say CO2 or some other waste, and it would cost too much to the contemporary environment, to the contemporary society, civilization, to perform or to generate electric power in such a plant. So they didn't thought of that prevention. It is too late now. It'll cost a lot of money to just get rid of that factory. Second is atom economy, and we will discuss that. We'll discuss that term in a moment. I mean the real meaning of the term, because we can design that, and basically it means that synthetic methods should be designed to maximize the incorporation of all materials used in the process into the final product. So basically, if we have reagent and we will just have here a certain atom configuration, basically we would like to have all of them here and not within the rest. So we can define an atomic configuration has a special meaning in chemistry, but I mean something set of atom to just include all of that within the product, and so maximize that and minimize that within the waste. So it is just a non-strict definition of the atomic economy, or atom economy is a real name, and it is surprisingly this term on this idea has appeared only in the just end of 90s, so relatively late time. Why? One should ask, why so late we realize the fact of need to maximize the atom economy, or the sum of, or the contribution of this atom or the reagents to the product and not to the waste. And I would say that the reason for that is quite obvious. So for years, I mean, our knowledge of chemistry, our art of creating chemical products was not perfect. So we have been fighting with nature, performing this synthesis, yeah, I mean number H, synthesis, yeah, I would say synthesis. It's a plural, yeah, or synthesis is singular in English. So synthesis is plural, many different synthesis procedures. And with the increase of the meaning of computers, databases, we realize that there are many different procedures, and that the environment is very important. The cost on the environment is very high, and we cannot afford creating a lot of waste, because then we are living not in a way we would like to. And it's much better to have a nice environment in lake or sea or forest than to have an industrial landscape with many chimneys, which is not good for our health. Then less hazardous chemical synthesis. Less hazardous, I mean less hazardous chemical synthesis, yeah, less hazardous chemical synthesis. I mean, wherever practicable, so when we can use that, synthetic methods should be designed to use and generate substances that possesses little or no toxicity to human health and to the environment. It is the literal sounds of this rule, and it simply means that we need better chemistry, new chemistry methods for that. It means also when research and design, or R&D, research and design, R&D, research and design in English, is very important. We need to invest a lot of money in that area. Then we can be at the top of chemical research, and we can design new methods for less hazardous chemistry. Let's say if we would like to use or get rid of the use of acid chlorides, which are often lacrimators and are not nice for the application in the lab. So lacrimators, what does lacrimators mean? Płaczemy po nich, yeah, in Polish. So we cannot do here without new research. Then design safer chemicals. Design safer chemicals. So number 4. Safer chemicals. So number 3 was less hazardous chemical synthesis, means very, very general rule, and we can perform the same reaction times, but let's say maybe chlorides would be better than bromides and so on. So chemical synthesis could be the same, but we can use different type of chemicals within that. So let's say maybe bromide are better than chlorides, or even completely different leaving group could be better than halogens, and this is then less harmful to the environment. And I mean, the rule is chemical products should be designed to affect their desired function while minimizing their toxicity. And not only toxicity, but also, I mean, the suitability. I mean, the chemicals should be suitable to work with them in organic chemistry lab or industry, and you worked and you are also working on your artwork during preparation of your thesis, and already you know that there are some chemicals that are not nice in the lab. Then safer solvents and auxiliaries. 5 safer solvents and auxiliaries. Auxiliary solvent. So we know what is a solvent. Solvent is, let's say, water or methanol or ethanol. And what is an auxiliary? Can anybody say what's an auxiliary? What is the difference between, let's say, the solvent and auxiliary? Let's say an auxiliary, if we perform, for example, the isolation of an enantiopure acid, and we use an amine in an enantiopure form. So enantiopure amine to make the diastereoisomeric salts. So we are using this amine only to allow the resolution of the enantiopure acid. So then the name will be auxiliary. Auxiliary. So we have, let's say, the acid in a form of 2 enantiomers, so 2 enantiomers, and we have 1 amine, let's say, or 1 it is one enantiomer, and then what we are producing are two diastereomers, two diastereomeric salts, yeah, which then will allow us to prepare enantiopure carboxylic acid. So in a form of a pure enantiomer, and this amine then is an auxiliary. We are using that in the synthesis only, but it is not a solvent. Its role in the synthetic is just and say auxiliary, some helping us, only. But basically, I mean, the real chemical structure of an amine has only a secondary meaning. It has a meaning because, let's say, some could form two stable enantiomers, then we cannot isolate the pure acid from that salt, or I mean, some would not be good enough for crystallization. So it has some meaning, but it's not of first order. So similar to solvent. To solvents also we should design or we should pick up such a solvent which will allow us to perform a reaction and to obtain high yield and so on and so on. However, it's only a solvent, yeah. So we have number 5, safer solvent like auxiliaries. So should be made unnecessary whether possible, and so we should use safer, and if possible get rid of that. So if possible to obtain an enantiopure product here without this auxiliary, and we can also follow, we can perform reaction in batch, for example. So put two substances together, let's say even in the even as powders without solvent. So if such procedure is possible, just go this way. Don't use solvents. It's every time it's just a waste, and time to time we can then of course purify the wasted amine here, but not always. Then we have number 6, design for energy efficiency. Design for energy efficiency.